Deep beneath the Earth's surface lies a mysterious world of molten metal and immense forces that shape our planet. In today's video, I'm counting down 15 of the most astonishing facts about the Earth's core. Let's start with number 15, magnetic reversals. The Earth's magnetic field acts like an invisible shield that keeps us safe from harmful cosmic rays from space. This field doesn't stay the same. Every few 100,000 years, it flips, switching the north and south poles. This flip, while not entirely understood, is closely linked to what happens deep inside the Earth's core. Here's how it works. Deep beneath the Earth's surface, about 1,800 miles down, is the outer core made of molten iron and other metals. This liquid layer surrounds a solid inner core. Now, the movement of these metals generates electric currents, which in turn creates this magnetic field. Now, it's this field that's what makes a compass point north. Over time, the movement of the metal in the outer core can get a bit messy and chaotic, and this chaos can cause the magnetic field to flip completely, a change that happens irregularly, and it's hard to predict. The last time this happened was about 773,000 years ago, in what is known as the Matuyama-Brunhes reversal. Recent studies have shown that this reversal took about 22,000 years to complete, much longer than the 4,000 to 9,000 years scientists originally thought. This suggests that the flipping process is more complicated and takes more tries than previously believed. Although scientists are still trying to figure out exactly why and how these reversals happen, they know that during a reversal, the magnetic field weakens significantly. This weakened field doesn't protect us as well from cosmic rays, which could increase radiation on the Earth's surface and cause problems with satellite communications and power grids. The full impact of these changes on life on Earth is still a topic of debate, but understanding these magnetic reversals is critical, as they could have significant effects on our technology-reliant world. Number 14. The age of the core. Not all parts of the Earth are created equal. It's made of many parts, some older than others, with the core being the granddaddy of them all. Scientific studies have placed the age of this inner core at around 1 to 1.3 billion years old, making it one of the oldest parts of our planet. But how is it possible for the core to be so ancient, and how do scientists determine that age? Well, understanding the age of the core not only reveals the history of our planet, but also offers insight into the origins of life itself. The Earth's core is a solid ball of iron surrounded by a liquid outer core that slowly churns, generating the planet's magnetic field. The reason the core is so ancient lies in its formation process. As the Earth cooled over billions of years, the molten iron at its center began to solidify, forming the inner core. This process started around 1 billion years ago, long after the planet itself had formed. As the planet loses heat to space, the cooling starts from the inside out, causing the core to crystallize first. This means that while the surface of the Earth continues to evolve and change, the core has remained relatively unchanged for billions of years. Now, determining the age of the Earth's core isn't easy. Scientists can't dig down there, so they rely on indirect methods. By creating the immense pressure and temperature found deep within the Earth in lab settings, scientists can estimate when the core began to solidify. Recent experiments involve squeezing iron between 2 diamond anvils and heating it with lasers, creating conditions similar to those in the core. These studies showed that the iron in the core conducts heat at a certain rate, which helps scientists estimate when the inner core started to form. The results suggest that the core is around 1 to 1.3 billion years old, placing it in the middle range of previous estimates. Number 13. It's mushy. So for decades, the Earth's inner core was believed to be a solid ball of iron, dense and unyielding, surrounded by a swirling liquid outer core. But recent research has flipped that notion on its head, revealing that the core is not as solid as we once thought. Instead, it turns out that the Earth's core is a strange mix of hard, semi-soft, and even mushy iron. But how can something buried so deep beneath our feet be anything but solid rock? Well, the Earth's inner core, sitting at more than 3,000 miles beneath the surface, has long been imagined as a tightly packed sphere of iron. After all, iron is heavy and solid at room temperature, so it made sense to assume that under the extreme pressures and temperatures found in the Earth's core, it would be even denser and harder. However, new studies suggest that the core is a bit more complex, with regions that are not only soft but also semi-soft and even partially molten. This softness at the core can be compared to a thick, sludgy material, solid enough to resist flow in some areas but soft and squishy in others. This unusual consistency is the result of extreme conditions at the core, where temperatures will reach over 9,000 degrees Fahrenheit and pressures are more than 3 million times that of the Earth's surface. So given that we can't physically reach the Earth's core, scientists rely on indirect methods to study it. The most powerful tool at their disposal? The analysis of seismic waves generated by earthquakes. Seismic waves come in two main types: compressional and shear waves. When large earthquakes happen, these waves travel through the Earth and can be detected on the opposite side of the planet. By comparing the speed and path of these waves as they travel through the core, scientists noticed something strange. The waves didn't behave as if they would if the core were entirely solid. Instead, the waves were deflected or slowed down in certain areas, suggesting that the core has softer regions, even mushy material. Number 12. Iron and nickel. So when we think about the Earth's core, it's easy to picture it as a bubbling sea of lava, thanks to countless science fiction movies and books. But the reality is far more complex and fascinating. The Earth's core is divided into two parts, the outer and inner. While both predominantly are composed of iron and nickel, they exist in very different states. The outer core is about 1,400 miles thick and it's made of molten iron and nickel. In this churning liquid outer core that generates the magnetic field through a process known as geodynamo, the inner core is a solid sphere with a radius of about 760 miles. Despite the extreme heat though, comparable to the surface of the sun, the immense pressures at this depth forces the iron and nickel to remain in a solid state. The discovery of this inner core dates back to the 1930s, when scientists first noticed that seismic waves behaved differently than expected, leading to the conclusion that the Earth's core had a solid center. The core isn't just a fascinating geological feature, it's crucial for life on Earth. The movement of the molten outer core generates our protective magnetic field that shields our planet from harmful solar radiation. The solidification of the inner core also plays a vital role in that process. As the inner core grows, it releases heat, which drives convection currents in the outer core, powering the geodynamo and maintaining the magnetic field. Number 11. Under pressure. While it's easier to imagine the Earth's core as a flow of liquid hot magma, it's actually a place of unimaginable pressure and heat, where conditions are so extreme that they could easily crush or vaporize anything from the surface. The core is a solid ball of crystallized iron, roughly the size of the moon, surrounded by a molten outer core. Despite being hotter than the surface of the sun, the intense pressure keeps the iron in the core solid. But what exactly happens under these extreme conditions, and how would that affect the human body if it were possible to venture there? The pressure at the Earth's core is about 3.5 million times higher than what we experience here at the surface. To put that into perspective, the weight of an entire atmosphere pressing down on us is only about 14.7 pounds per square inch. At the core, the pressure is around 52.5 million pounds per square inch. This pressure is beyond anything we can truly imagine. While the iron on the surface has a relatively simple crystal structure, deep in the Earth's core the atoms are forced into a much denser arrangement. If you were somehow transported to the Earth's core, the outcome would be immediate and devastating. Forget about the heat, the pressure would crush you instantly. The human body, which is mostly made up of water and soft tissues, would have no chance of withstanding such forces. Every cell in your body would be compressed into a fraction of its size, and you would be reduced into a dense mass almost instantaneously. Squish. But beyond the pressure, the temperature at the core is around 10,000 degrees Fahrenheit, hotter than the surface of the sun. Even if you could somehow survive the pressure, the heat would turn a human into gas and then evaporate them in a matter of faster than Thanos can snap his fingers. The iron at the core remains solid only because the pressure is so great that prevents the atoms from moving freely and turning into a liquid. Number 10. Hotter than the sun. As I've already mentioned, the Earth's core reaches staggering temperatures. Astonishingly, the Earth's core is hotter than the surface of the sun, a fact that changes our understanding about what lies beneath our feet. These temperatures go up to around 10,800 degrees Fahrenheit. Now, to put that in perspective, the surface of the sun is about 9,930 degrees Fahrenheit. This means that the Earth's core is around 870 degrees hotter than the surface of the sun. So we'll start from the beginning. When the Earth was formed around 4.5 billion years ago, it was a molten mass of rock and metal. The process of this formation involved countless collisions and mergers of planetesimals, small celestial bodies, which generated an enormous amount of heat. The core is also heated by the decay of radioactive isotopes like uranium-238, thorium-232, and even potassium-40. These elements release heat as they break down, a process that continues over billions of years, maintaining the high temperature. The heat from the core plays a critical role in shaping our planet. It drives the movement of tectonic plates, which float on the semi-fluid mantle above the core. This movement causes earthquakes, volcanic eruptions, and the creation of mountain ranges, all of which have a profound impact on the surface. As heat from the core radiates upwards, it causes convection currents in the mantle. Now, these currents are slowly moving the plates of the Earth's crust, a process known as plate tectonics. Without this heat-driven movement, the Earth would be a static, lifeless planet, and that wouldn't be very fun, now would it? Well, while the Earth's core has remained hot for billions of years, it is slowly cooling. However, this process happens over such an extended timescale that it's virtually imperceptible in human terms. The core cools by about 100 degrees Celsius every billion years, meaning it could take another billion years for it to cool by any significant amount. The Earth's core has been cooling since the planet's formation, and while radioactive decay continues to generate heat, it's not enough to increase the core's temperature over time. Number 9. Hollow Earth? The hollow Earth theory is one of those tantalizing ideas, despite its clear contradictions with established science, and has managed to captivate the imagination for centuries. At its core, no pun intended, the theory posits that our planet is not a solid sphere, but rather a hollow shell, with vast empty spaces or even entire civilizations existing beneath the surface. While the idea is intriguing and has inspired countless works of fiction, it ultimately falls apart under the weight of modern scientific understanding. From ancient times, the notion of a world beneath our feet has held a powerful allure. From the ancient Greeks, the underworld was a realm of the dead, a dark and mysterious place that existed beneath the crust. These early concepts were largely metaphorical, representing the afterlife or place of myth rather than a physical reality. However, in the 17th century, the hollow earth theory began to take on a more scientific guise, gaining traction among some of the leading thinkers of the time. One of the earliest scientific proponents of the hollow earth theory was that of Edmund Halley, the astronomer best known for Halley's Comet. In 1692, Halley proposed a radical idea to explain certain anomalies in compass readings. He suggested that the Earth was composed of a series of nested spherical shells, all revolving around a central core. While Halley's theory was imaginative, it was also based on fundamental misunderstandings of the Earth's structure, a misunderstanding that has since been thoroughly debunked. In the end, the hollow earth theory is a fascinating example of how human curiosity and creativity can lead to fun, if not misguided ideas. While it is kind of fun to imagine a world within our world, populated by mysterious beings or even advanced societies, the Earth is in fact anything but hollow. Number 8. The Gutenberg Discontinuity. So deep beneath the Earth's surface lies a boundary that's intrigued scientists for over a century: the Gutenberg Discontinuity. Now, this is a remarkable discovery made by German seismologist Benno Gutenberg in 1913, and it's greatly enhanced our understanding of the Earth's interior and the dynamic processes that shape our planet. Yet despite its significance, this boundary still holds many mysteries. The Gutenberg Discontinuity is a transition zone located approximately 1,800 miles beneath the Earth's surface, where the solid lower mantle meets the liquid outer core. This boundary isn't a single sharp line, but rather an uneven, narrow zone that varies in depth and structure. It represents a profound change in the Earth's internal composition and marks the point at which seismic waves, vibrations generated by earthquakes, behave very differently. Gutenberg, born in 1889, was a pioneering seismologist who dedicated his career to studying the Earth's inner layers. In 1913, he made a groundbreaking observation. At a certain depth beneath the surface, the behavior of seismic waves changed dramatically. Primary waves, which can travel through both solid and liquid, slowed down significantly, while secondary waves, which can travel only through solid material, disappeared entirely. This observation led Gutenberg to the conclusion that at around 1,800 miles deep, the Earth transitions from a solid state to a liquid one. This established the boundary now known as the Gutenberg Discontinuity. This boundary has helped scientists to better understand the structure of the Earth, including the existence of the outer core, which is composed of molten iron and nickel. Despite its importance, though, the Gutenberg Discontinuity does remain shrouded in mystery. One of the key questions that scientists continue to explore is how this boundary changes. The intense heat within the Earth causes the core to gradually cool and solidify, which could lead to changes in the position and characteristics of this discontinuity zone. Moving on to number 7, olivine. In the layers beneath the giant onion that we call the Earth, a mineral called olivine plays a critical role in unlocking the mysteries of the planet's interior. Found deep within the Earth, often in the mantle, olivine is a silicate material that provides scientists with essential clues about the composition and history of the Earth's layers, particularly those below the crust. Olivine is a magnesium-iron silicate with a distinctive greenish hue, ranging from olive to emerald green, which is where it derives its name. The presence of olivine is particularly prominent in peridotite, a rock that dominates the upper mantle. This mineral is not only abundant in the subsurface, but also found in meteorites, offering a small glimpse into the building blocks of the solar system. Now, olivine is most commonly found in the Earth's mantle, which lies between the crust and the core. While the mantle is typically inaccessible due to its depths, olivine can be brought closer to the surface through volcanic eruptions or tectonic activity. Additionally, oceanic drilling projects have allowed scientists to retrieve samples of olivine from beneath the seabed, particularly in regions where the Earth's crust is thin. Accessing olivine-rich mantle rocks ain't easy. Most of the Earth's mantle lies tens of miles beneath the surface, far, far out of reach of conventional drilling. However, in places where tectonic plates diverge, such as the Mid-Atlantic Ridge, the mantle can be exposed or brought closer to the surface. This was the case with the Atlantis Massif, where a scientific expedition managed to drill deeper into the Earth's mantle than ever before, retrieving a nearly intact core of olivine-rich rock. This monumental achievement has provided scientists with invaluable data and samples for studying the Earth's internal processes. Number 6. Life comes from the crust. The origins of life on Earth are inextricably linked to the planet's crust, a connection that reveals the profound impact of geological processes on biological evolution. This seemingly simple layer of rock beneath our feet has played a critical role in nurturing the early conditions that allowed life to flourish, shaping the trajectory of biological complexity over billions of years. The Earth's crust, the outermost solid shell of our planet, is more than just a foundation for life. It is the birthplace of life itself. This concept suggests that the earliest forms of life may have emerged from the unique environments created by the crust, particularly in hydrothermal systems and other geothermal hotspots. The Earth's crust is composed of a rich variety of minerals and elements, many of which are essential for life. When combined with water, these minerals can undergo chemical reactions that produce the building blocks of life, such as amino acids and other organic molecules. These reactions are intense in hydrothermal systems, where heat from the Earth's interior interacts with the water and minerals in the crust. 4 billion years ago, the Earth was a pretty violent place, frequently bombarded by asteroids and comets. These impacts were not only reshaping the planet's surface, but they also contributed to the foundation of vast hydrothermal systems. These systems were likely widespread and may have been some of the earliest habitats of life. The high temperatures and rich chemical environments in these systems would have been ideal for the formation of simple, heat-loving organisms known as thermophiles. The process of life's emergence from the Earth's crust was gradual and complex. Initially, the heat from asteroid impacts and volcanic activity created a hostile environment, but as the planet cooled, the conditions became more favorable. In the deep ocean ridges where the crust is thinner and the mantle closer to the surface, tectonic activity created mid-ocean ridges and hydrothermal vents. These vents released hot, mineral-rich water into the ocean, providing the perfect environment for life to begin. Number 5. Is it leaking? Recent discoveries have revealed that the core is not as isolated as once thought. It's leaking. This leakage has profound implications for our understanding of the planet's internal dynamics and its long-term evolution. When scientists say that the Earth's core is leaking, they're referring to the slow transfer of materials, particularly certain elements from the core into the mantle, the layer of thick rock surrounding the core. This process has been happening for billions of years, but it's only recently that we've gathered enough evidence to confirm it. Now, the leak primarily involves elements like tungsten, which is found in different isotopic forms. By studying the ratios of these isotopes in volcanic rocks, researchers have been able to trace the movement of tungsten from the core into the mantle. So we've talked a lot about the iron core today, but there are some more elements within the core: tungsten, platinum, and gold, all of which are known to dissolve in iron-nickel alloys. The leak involves the migration of these elements, particularly tungsten, from the core into the mantle. This leak suggests that the Earth's core and mantle are more interconnected than previously thought, with materials slowly moving between these two layers over geological timescales. The leak of materials from the core to the mantle is thought to be driven by two main processes, the first of which is the mantle plume. These are upwellings of hot rock that rise from the core-mantle boundary to the Earth's surface. As the plumes ascend, they bring core material with them, including tungsten. Mantle plumes are responsible for creating volcanic hotspots like those in Hawaii and Iceland, where this core-derived material can sometimes be found in the rocks. The next process is called subduction and oxygen increase. Here, the tectonic plate boundaries, the slabs of Earth's crust that are pushed down into the mantle in a process known as subduction. These slabs carry oxygen-rich materials into the deep mantle. Now, experiments suggest that increasing oxygen concentrations at the core mantle boundary can cause tungsten to separate from the core and migrate into the mantle. Well, the core has been leaking for at least 2.5 billion years, according to studies of tungsten isotopes in ancient rocks. But before this period, during the first 1.8 billion years of the Earth's history, there seems to have been little or no transfer of material from the core to the mantle. This suggests that the Earth's interior dynamics have changed significantly over time, with the onset of more vigorous mantle convection and tectonic activity potentially triggering the leakage. Number 4. The Kola Super Deep Borehole. Those who are old enough to remember may recall the space race between the US and the USSR, but we don't often hear about the inner space race. While we've sent probes like Voyager 1 billions of miles beyond our solar system, our attempts to penetrate the Earth have barely scratched the surface. The Kola Super Deep Borehole, located on Russia's Kola Peninsula, represents the deepest point ever reached by human drilling, extending 7.5 miles down into the Earth. Now, despite this impressive depth, it only penetrates about a third of the way through the continental crust and a mere 0.2% of the Earth's total radius of almost 4,000 miles. The project was a part of a less publicized Cold War race between the US and the USSR, where the two superpowers sought to explore the Earth's depths in a bid to outdo each other in scientific achievements. Well, the US abandoned its efforts with the Project Mohole due to funding issues, but the Soviet Union persisted, eventually creating the Super Deep Borehole. Despite this, the borehole remains just a tiny dent in the Earth's layers, a reminder of how much remains unknown. This borehole revealed unexpected conditions and scientists ventured deeper. At depths of around 33,000 feet, temperatures soared to over 356 degrees Fahrenheit, much higher than the 212 degrees that scientists had predicted. These extreme temperatures, combined with increasing rock porosity, transformed the rock into a plastic-like state, making further drilling nearly impossible. One of the most remarkable findings, though, was the discovery of microscopic fossils in rocks over 2 billion years old. These fossils, encased in organic compounds, survived under immense pressure and heat, offering direct evidence of ancient life deep within the Earth's crust. This finding was not only unexpected, but also raised new questions about the history of life on our planet and the conditions in which it can persist. Number 3. The mantle is recycling oceanic crust. Kurtal recycling is a process that's been going on beneath our feet for billions of years. It's basically the Earth's way of renewing its crust, like how we recycle materials to make new things. Scientists recently found out that this recycling happens much faster than we initially thought, about 500 million years instead of the 2 billion years previously believed. Kurtal recycling refers to the process where the parts of the Earth's crust that are pushed deep down into the mantle later reappear at the surface. Imagine the Earth's crust as a conveyor belt. Sections of it get dragged down, melted, mixed with mantle minerals, and eventually resurface. This process has been happening for as long as the Earth has had tectonic plates, but thanks to some new research, we know it can happen much faster than we thought. Scientists figured this out by studying volcanic rocks from Mauna Loa in Hawaii, the largest volcano on Earth. By examining specific elements like strontium isotopes in these rocks, they were able to track how old the material is and where it came from. In regions like the Pacific Ocean's Ring of Fire, earthquakes and volcanic eruptions are common, and they're the direct evidence of the ongoing recycling process. But what's surprising is that this whole cycle from surface to mantle and back can take as little as 500 million years. Forces push and pull the plates around, causing some to dive down into the mantle, and once there, the crust material heats up, melts, and mixes with it. Eventually, the material finds its way back up to the surface, usually through volcanic eruptions. This process helps keep the Earth's surface dynamic and constantly changing. It also plays a big role in the planet's ability to regulate its temperature and recycle essential materials like water and minerals. They're crucial for life. Number 2. Core collapse. The core collapse theory, it's an idea that gets thrown around in discussions about Earth's future, and it might sound like something out of a science fiction movie, but what does it actually mean? Has Earth's core ever collapsed? Is it even possible? Well, core collapse theory suggests that the Earth's core, the solid and liquid iron-nickel center of our planet, could fail or collapse in some catastrophic way. This could happen if the processes that generate Earth's magnetic field were to stop working correctly. The magnetic field is essential. It acts like a shield protecting us from harmful solar radiation. But no, the Earth's core has never fully collapsed. However, scientists have discovered that Earth's magnetic field, which is generated by the motion of molten iron in the outer core, has almost collapsed before. About 591 million years ago, the magnetic field weakened dramatically and it nearly failed. This was a close call, but instead of collapsing, Earth's core managed to stabilize and strengthen, likely due to the solidification of the inner core. While a full collapse of Earth's core is unlikely, the weakening of the magnetic field is not only plausible, but has happened in the past. The field's strength fluctuates over time due to changes in the flow of the molten iron in the outer core, and those fluctuations, if they were extreme enough, could lead to a significant weakening of the field. However, a total collapse of the core, as in a scenario where the core stops functioning altogether, is highly improbable given our current understanding of Earth's geodynamics. If Earth's core were to collapse, or even stop generating a magnetic field, we would see some dramatic effects. The most immediate impact would be the loss of our magnetic field, which would expose the Earth to intense solar radiation. Without it, the Earth's atmosphere would gradually erode, potentially leading to a loss of water and other essential gases. The loss of this field could also affect the Earth's climate, potentially causing more extreme weather patterns and shifts in temperature. These changes would make the Earth a much more hostile place for life, possibly leading to a mass extinction, similar to events that happened during the past geomagnetic reversals. Number 1. Its changing rotation. The Earth's core is often viewed as a stable, unchanging part of our planet, but recent research suggests it might be more dynamic than we previously thought. Scientists have found that the Earth's inner core, a solid sphere of iron and nickel, may be changing the direction of its rotation. The Earth's inner core rotates within the outer core. Now, this rotation happens because the Earth itself is spinning, and the inner core is somewhat decoupled from the rest of the planet due to the fluid outer core surrounding it. Normally, the inner core rotates slightly faster than the Earth's surface, a phenomenon known as superrotation. Now, this rotation isn't perfectly synchronized with the mantle and crust due to the different physical properties and the dynamic environment of the core. Researchers analyzed seismic waves from earthquakes, which travel through the core to detect changes in its rotation over time, and they found that while the core was spinning faster than the Earth's surface from the 1970s to the 2000s, it began to slow down around 2009. Now, it might be rotating more slowly than the rest of the planet. This change in rotation isn't dramatic. It's measured in tiny fractions of a degree per year, but it's significant enough to be detected by sensitive seismic instruments. The idea that the inner core's rotation might change over time isn't entirely new. Some scientists have hypothesized that the core's rotation could oscillate, changing direction every few decades or so. However, this is still a topic of debate, with different studies suggesting varying rates and patterns of rotation. For example, while some researchers have proposed that the core could shift its rotation direction every 6 years or so, others believe that the core might rotate at a consistent rate, with occasional lurches or shifts. In any case, the potential change in the core's rotation is intriguing, but it doesn't pose any immediate threat to life on Earth. The core's rotation, though, could influence the planet's magnetic field, which protects us from harmful solar radiation. One possible effect of the core's slowed rotation is a slight alteration in the length of Earth's days. If the inner core continues to decelerate, though, it might cause the Earth's rotation to slow down as well, leading to slightly longer days. But this change would be minuscule, on the order of milliseconds over many years, so it's not really something we are ever going to notice. Thanks for watching, everyone. I'll see you next time. Thank you to our channel members.